In the previous video, we just went over the general reaction scheme for the Wittig reaction. So we have an aldehyde or ketone with an ylide reagent, and that forms an alkene, or in other words, an olefin, where we have a new carbon-to-carbon bond formed. That's our desired product, and then a byproduct is this really stable and soluble triphenylphosphine oxide. So let's talk more about this ylide reagent here. This is new to us. An ylide is a carb anion Remember, a carb anion is a carbon atom with a negative charge. That means it has a lone pair and 3 bonds. So this is a carb anion that is stabilized by resonance. Let's draw that resonance out here. So our ylide has 3 phenyl rings bonded to a phosphorus. The phosphorus is double bonded to carbon, and then carbon has its 2 other single bonds. So phosphorus double bonded to carbon. Phosphorus has 3 phenyl rings. And then carbon has 2 R groups. I'll be consistent and use R prime here. So phosphorus is a hypervalent atom. It's in the 3rd row of the periodic table. So just like sulfur, like silicon, it can hold more than 8 electrons in its valence shell. And you might notice here, phosphorus has 5 bonds. So that means there are 10 electrons in the valence shell in the structure that's drawn here. So phosphorus, 3rd row element. It is hypervalent, meaning it can hold more than 8 electrons in its valence shell. Well, phosphorus is also stable with only 8 electrons in its valence shell, and we can achieve that through resonance in the structure here. The only bond that can resonate directly from the phosphorus, the way we've drawn it here, is this pi bond between phosphorus and carbon. So this pi bond can break and will keep carbon's valence shell full, so it has 8 electrons in its valence shell. Phosphorus, as a result here, would have 8 electrons in its valence shell instead of 10. So this is another stable resonance structure. So phosphorus will have 4 single bonds. 3 of them are to phenyl rings. And then the last one's to the carbon. The carbon has its 2 single bonds to R groups. It has a lone pair of electrons and a negative charge. And the phosphorus has a positive charge. Now remember, the phenyl rings are electron donating groups through resonance. I won't show that resonance here, but you might imagine that a pi bond from a phenyl ring can resonate. And that way that positive charge is delocalized across phosphorus and all of the atoms in the phenyl rings. So this is a resonance stabilized carb anion structure. So here's our carb anion. Again, resonance stabilized, just like when we did our previous reactions in this unit with enolate ions. We have a negatively charged carbon in enolate ions that is stabilized by resonance. It's the same idea, but in this case, the carb anion is stabilized by resonance with the phosphorus. So there are a few ways. We'll talk about 2 ways to form this ylide molecule. So we'll show reaction 1 to form the ylide. So forming the ylide that reacts with an aldehyde or ketone to form the alkene. And then, so we'll show 2 different ways to form them. We start with triphenylphosphine. This is a stable molecule that can be purchased. So we have a phosphorus bonded to 3 phenyl rings. I'm just abbreviating with a pH for phenyl. This is triphenylphosphine. So we have a phosphorus with lone pair of electrons. If we have our solution of triphenylphosphine and then add an alkyl halide with a good leaving group, here's an example of a methyl, the bromine. Remember, this carbon to bromine bond is very polar. We have non-bonding electrons here on the phosphorus. So this would do a simple substitution reaction. Where we'd have the phosphorus still bonded to the 3 phenyl rings. And then now that phosphorus is bonded to the CH3 group, and bromine is the leaving group, so it leaves as an ion. In this case, phosphorus with 4 bonds has a positive charge. Phosphorus is in the same column as nitrogen, so it has similar formal charges as nitrogen would. So with 3 bonds in a lone pair, it's neutral. With 4 bonds, it is positive. Here we have not formed the ylide yet. We are almost there. We need to remove a hydrogen from the CH3 group. If we draw out the bonds, we currently have 3 carbon and hydrogen bonds. We need to remove one of these hydrogens. That means we need a strong base. A strong base that can be used here that's often used for formation of ylides is butyl lithium. So CH3, CH2, we have 4 carbons, and then a lithium. This is done in a aprotic solvent, so something like diethyl ether or hexanes. Some aprotic solvent can be used here. And this is because butyl lithium, strong base. It reacts violently with water. It's an extremely exothermic reaction and produces butane. This reaction will also produce butane when we add it with that phosphorus and carbon compound. Remember, butane is the liquid that's in lighters. And so if there is a spark or if there's enough heat, that butane can ignite. That can be explosive and extremely dangerous to work with. So butyl lithium is handled without water to avoid any explosions. So very, very careful. Chemists are really careful as they're working with butyl lithium. Because this is a strong base, it can remove one of the hydrogens from the CH3. And that would produce if we remove a hydrogen, then we've got a lone pair on that carbon. And this is the ylide. This is the structure, the resonance structure of the ylide with the carbon having a negative charge. Byproducts of this step are lithium bromide, and butane. Okay, so that's one way to form an ylide. We start with triphenylphosphine oxide, add an alkyl halide with a good leaving group, so bromine or chlorine. That forms this compound here. We need to remove a hydrogen from the carbon, so we use a strong base, butyllithium. It's not a very acidic hydrogen, so that's why a very strong base is needed when you form the ylide. Another way, the second way that we'll discuss to form an ylide is through using an alpha haloester. So, second option with an alpha haloester. So again, we have triphenylphosphine. And we have an alpha haloester. So we have an ester, which is a carbon to oxygen double bond, and that carbon's bonded to an oxygen, and that that oxygen has another carbon chain. We'll make it an ethyl here. Then the alpha carbon to the carbonyl is bonded to a bromine. So remember, this is the alpha carbon in a structure with a carbonyl. So this is an alpha bromoester. Just like the previous reaction, the first step is a substitution where the phosphorus can bond to the alpha carbon and the bromine will leave. So now we have phosphorus bonded to the alpha carbon. The rest of the molecule is the same. And we have the 3 phenyl rings. And we have a positive phosphorus. Now, again, we need to remove a hydrogen from the alpha carbon to produce the carb anion. Now, remember, if we have an alpha carbon, those hydrogens are more acidic. They're slightly acidic. So we have acidic alpha hydrogens here. Oops. So the benefit of using an alpha haloester is that you do not need to use the strong and dangerous base butyllithium. These are more acidic, so a weaker base can be used than butyllithium. Something like sodium hydroxide can be used. Just adding our leaving group there. So we can use something like sodium hydroxide and in water, because these are slightly acidic hydrogens, so something like sodium hydroxide will work, and we will have, I'm going to abbreviate now and just do pH with a subscript 3 to represent the 3 phenyl rings bonded to phosphorus. Now that carbon here, the alpha carbon, has lost 1 hydrogen, so it has a lone pair and a negative charge. Phosphorus still has a positive charge. And we have the ester group. So here's the ylide. And the only other byproduct here would be water, which is in solution anyway, because we would take an OH minus, and remove an alpha hydrogen. So let's write this benefit here. Benefit of using an alpha haloester. You can form the ylide with a weaker and a safer base. We don't have to worry too much about explosions when we're working with sodium hydroxide. Okay, so these are 2 ways to form ylides. In the next video, we'll show the Wittig reaction mechanism using an ylide and reacting it with an aldehyde or ketone.